My name is Luis Yamin, and I am a member of the Natural Risk Assessment Consortium Latin America. I have responsibility for developing the Central American Probabilistic Risk Assessment CAPRA platform for the World Bank and the Inter-American Development Bank.
We will now show the software developed for the CAPRA platform and the formats normally used by this platform. The CAPRA platform is composed of a series of modules consisting of different software components. In principle, the platform utilizes 4 different groups of software packages. These groups are the hazard module, the exposure module, the vulnerability module, and the risk module. Each software group includes a series of tools facilitating specific use of the platform's different options. We will now quickly review the main software components for evaluation of a typical risk assessment project that is organized in the same way that the software is used. That is, first, assessment of the risk with any of the tools. In particular, assessment of seismic, rainfall, hurricane, flood, landslide, or volcanic risk. This is followed by the different modules for gathering exposure data and then vulnerability data for each component to be modeled. And lastly, the general module for data integration and for final assessment of the risk. The following is a list of the main modules utilizing the CAPRA platform for hazard modeling. The Crisis 2007 program for seismic and tsunami hazard assessment, the ERN Hurricane module for hurricane hazard assessment, the ERN Non-Hurricane Rainfall module, the ERN Landslide module, the ERN Flood module, and the VHAST module for volcanic risk assessment. These are the main hazard assessment components. For compiling exposure data, a series of web-based data gathering tools is available, essentially based on Google Earth. For vulnerability, we have the ERN Vulnerability module. For risk assessment, we then have the CAPRA GIS platform, which integrates all the above-mentioned hazard, exposure, and vulnerability components for module integration and specific risk analysis. Lastly are a series of supplemental tools such as FileCat, software for classifying, visualizing, and editing data files in the different formats used by the CAPRA platform. The CAPRA software therefore consists of the different hazard, exposure, and vulnerability components, and each of these modules generates files in different formats for final integration into the CAPRA GIS platform. In general, the hazard module generates what we call the .ame format, which includes all hazard scenarios generated with these modules and enables a comprehensive probabilistic assessment to be generated for all possible scenarios considered for a hazard. The exposure module enables data to be gathered in shapefiles for representation of the different exposed components subject to the action of the different hazards analyzed. Lastly, we have the vulnerability module, which generates files in the .dat format for connection with the main CAPRA GIS tool or main CAPRA GIS platform. This links the above-mentioned modules and analyzes risks. All desktop programs have open-source Apache 2.0 licenses, so that the user may use the software for any purpose without commercial applications. All programs are available in Spanish and English. They may be used with the Microsoft Windows XP operating system or higher. They are written in Visual Basic. For all desktop programs, the technology is Microsoft .NET Framework. All web-based programs are also public domain. They are available mainly in Spanish. They may be used with any operating system chosen by the user. All are written in HTML and use mainly JavaScript and Google Earth technology. The main modules are summarized below. For seismic and tsunami hazard assessment, we have the Crisis 2007 program, developed mainly by Professor Mario Ordaz at the National Autonomous University of Mexico. It evaluates these hazards by generating stochastic events at any coordinates in the area of study. Modeling is based on the integration of occurrence frequencies for any intensity parameter. Like all the others, this program includes a user guide and technical reference manual that any user may enter and see details of how it operates, the type of data to be entered, and the main results obtained with each of these software programs. The ERN Hurricane module is used to analyze different types of hurricane-associated hazards, such as hurricane wind, storm surge, and hurricane rainfall, the three main hazard components included. For each component, the software generates hazard graphs for the different hurricane families included in the analyses and for different intensities associated with each of these phenomena, such as maximum wind speed, maximum flood depth from storm surge, and maximum intensity of rainfall associated with hurricane rainfall. In turn, each module generates its corresponding .ame format or file, which would then represent the series of stochastic scenarios for each event for completion of the hazard assessment. As for the others, the non-hurricane rainfall module generates a family of stochastic events or storms based on the hydrological representation of the area of study. A specific number of storms can be generated depending on user interest, and the module also generates an AME file with the representation of storms in the area of interest. Like the others, the flood module generates stochastic flood scenarios based on Ames files of rainfall, hurricane or non-hurricane. The method constructs unitary hydrograms at the mouth of the basin based on its characteristics and analyzes flood situations for each precipitation event. It then generates a series of related stochastic events with flood scenarios for comprehensive modeling of the hazard in the area of analysis. The ERN landslide program includes several analysis model options. First, the Mora-Varsin method for estimating susceptibility to landslides in areas of study. Newmark's method for estimating susceptibility to landslides and expected movement for different seismic hazards on slopes susceptible to movement. And the more traditional infinite slope and spherical failure methods for assessing susceptibility to landslides on more traditional slopes. The trigger factors or methods are mainly earthquakes and rainfall, and like those mentioned above, the model generates .ame formats, in this case with different landslide scenarios, or scenarios of susceptibility to landslides for the areas of interest. The VHAST module for volcanic hazard analysis is used to model ash fallout, lava flow, and pyroclastic flow events. Probabilistic modeling and deterministic modeling can be generated for specific scenarios, and like those mentioned above, .ame formats are then generated with the results of the hazard assessment for each event considered by the module. For vulnerability, we have the ERN Vulnerability Program, which generates, edits, or simply visualizes the vulnerability functions to be used in risk analysis. In this case, the system includes a series of vulnerability functions, published and generally accepted by the community, which users can access directly from the functions library and use in their analysis or edit and modify them to adjust to the specific vulnerability conditions of the study they wish to conduct. The system also estimates vulnerability functions based on the capacity curves of typical structures that users have generated with other methodologies. The COPRA GIS Risk Analysis module automatically records the vulnerability functions generated with this module in the required formats for purposes of comprehensive risk analysis. For exposure, a series of Google Earth-based tools are included for identifying and representing system infrastructure components or components of databases of exposure, structures, roads, and bridges. In general, the main characteristics of any infrastructure component that can be identified in aerial photographs or satellite images can be selected, located, and defined with this tool for inclusion in the exposure analysis database. Different types of tools are available to users, normally generating shape formats, which represent as dots, lines, or polygons, each element representing an exposed element with its specific characteristics for subsequent risk analysis. Lastly, we have the COPRA GIS tool, the fundamental risk analysis tool. It makes it possible to visualize all available geographic and exposure data and to read .aim, .shape, or .grd formats. Additionally, the system simultaneously enables specific projects defining a hazard to be identified, as well as an exposure database and a series of vulnerability functions so that the risk in a specific case can be assessed. Simultaneously, after the risk analysis has been performed, the tool makes it possible to visualize and fully edit the risk results so that the user has a very powerful tool for visualization, editing, and generating reports on hazards, exposure, and results of risk assessments. Where different types of files are available and a large number of projects are analyzed simultaneously, supplemental tools such as FileCat enable users to edit, visualize rapidly, and classify files for preparation of the data required for analyses and adequate interpretation of results. These supplementary tools are in the public domain, making these benefits available to users to improve their capacity to prepare information and interpret results. As regards formats used by the different modules, for hazards, .ame formats are used. These are geo-referenced binary raster files for consideration of all hazards from a multi-scenario perspective, i.e., including all possible hazard scenarios in a single file. .shape formats are used for representation of the exposure of exposed elements. FVU formats are used for vulnerability functions, and the associated .dat formats to assign vulnerability functions to each exposed component in the functions or in exposure databases. Lastly are the CPV risk formats, which include all data associated with a specific risk assessment project. .shape formats associated with exposure formats with the specific risk results for each component defined in these formats. And RES formats, which summarize and include supplementary data from risk assessment results, especially loss exceedance curves and other specific risk assessment results. .ame formats include a representation of stochastic scenarios with the characteristics indicated here, which, to summarize, include all possible scenarios comprehensively representing a hazard in a specific area.
This format enables several intensity measurements to be included with different statistical moments representing the event and with an annual occurrence frequency for each characteristic event. Dot shape formats receive data as dots, lines, and polygons for representation of different exposure components. They include variables such as physical exposure and human exposure, and must therefore include the vulnerability functions associated with each component, translated into additional fields which represent the structural system for each hazard defined.
Que representan el sistema estructural para cada una de las amenazas definidas.
These files define each vulnerability function for each type of hazard. These are the characteristic formats in terms of organization of the information these types of general files contain, which allow users to make specific editing if necessary, if they do not wish to do so directly with the available software, and then enables them to access all data in the files in terms of how it was generated, what information was used in generating it, and what specific data is used for each analysis made.
Cada uno de los análisis que se realizan.
Like dot shape formats, DAT formats describe in detail the vulnerability functions assigned to each component, and RES format include the risk results for the entire analysis portfolio. The dot shape format includes, in the case of risk analysis, specific units for representing the results of the assessment in terms of physical losses, monetary losses as units, or human losses, and relative associated losses. As mentioned above, these parameters are annexed to the dot shape format to achieve a representation of the risk of the different exposed elements.
All
COPRA platform software is fully open source and can be downloaded directly from the COPRA platform web page. It includes manuals in Spanish and English, short courses, training material, and specific examples. And all is designed for easy and prompt use so that users can make risk assessments simply, easily, and with maximum support from the platform standpoint. Users have responsibility for all analyses to be made as regards the use and limitations of a risk assessment. These are always to be used for important purposes and so should be evaluated by the user. This, then, is a general summary of the software included in the COPRA platform. Full in-depth information may be found in each user manual and on the platform's web page.